now. Okay. Good. So it is a pleasure to introduce Laura Scull. She will speak about mapping objects for Orbispaces. Thank you, Laura.
Okay, and I just want to start by thanking the organizers for putting this together and giving us a chance to get together and see each other, even if only by Zoom. So this talk is based on work that has been going on for quite a while. So Dorette and I started looking at Orbispaces and thinking about mapping spaces as part of a project that was a Women in Topology project. So we got together with the team in Banff. We were actually in Banff, not Zooming Banff. It was awesome. And bashed through a bunch of examples and really kind of started digging into what do Orbispaces and mapping spaces look like. And at the time we thought, oh, well, once we get this sorted out, we're just going to slap a topology on it and it's going to be awesome. Well, 5 years, 6 years later, we think we finally have the topology for this thing. It's taken us on quite a journey and some detours through some bicategories of fractions results and stuff like that. But we're really excited to finally have this sort of understood and nailed down. But I do want to give a shout out to my original team, Vesta Kufel, Carmen Roby, and Courtney Thatcher, who were awesome at just helping us think through the basics of this. And yeah, that was an awesome experience. Okay, so I'm going to be talking about something called Orbispaces, which are like Orbifolds, if you know Orbifolds, except that we're going to be ignoring the differentiable structure. So we're really just interested in the topology. But Orbispaces are spaces that have some symmetries on them, but it's going to be reasonably well-behaved symmetries. We're not going to go crazy and talk about stacks or anything like that. So really, we're just talking about finite group actions. Okay, so you could have a nice wallpaper pattern, for example, and you could take the quotient of that action on your wallpaper, and you would get a nice little Orbispace. Okay. So here's some examples. So it's important when we talk about the Orbispaces that we're not just ignoring the information that came from that group action or the local isotropy structure. We want to keep that. We want to remember what kind of singularity structure do we have locally. Even though we're throwing away the differential structure, topologically, we'd still like to keep that information. So this is an example where we could take a nice disk and we could roll it around itself, and we would get a nice little cone. And most of the cone would just be ordinary stuff. If you were living in this cone, there wouldn't be a whole lot going on. It would just be sort of manifold Euclidean-like. But then something weird is happening at that cone point. We would have that, if I did an order 3 rotation and rolled it up like that, I would have an order 3 point there. So that's the sort of information that we want to keep. We don't want to just say, oh, well, we have a cone, but we could flatten it out. Well, we could flatten it out, but we don't want to just ignore that information. We want to keep information about the isotropy structure. Okay. So now, of course, you don't have to have any isotropy structure. You could take any old manifold and consider it as an Orbispace and just say, oh, well, it didn't have any isotropy. Okay, so that's a big class of examples. Here's an example that's similar to the cone, but now instead of just doing the cone, we've actually capped it off. So this is a sphere. It's a 2-dimensional structure. It's kind of supposed to be hollow, but now, so we've got the cone point at one end, and then it rolls around itself all the way to the other, and it still has one singular point, and then the rest of it is kind of manifold-like. And then here is what you get if you wrap up those lizards that we had in my first slide. You get quite a bit of interesting isotropy structure. So the middle of the lizards is that gray area that I've shaded in. That's the part that doesn't have any isotropy. Those are kind of just the ordinary parts of your world. But now as you get along to the boundary, you've got these ZMUD 2 reflection lines appearing that have been rolled over on themselves. And then as you get to the corner pockets of my triangular billiard table, things get even stranger. You've actually got a dihedral action happening on the edges of those. So we can see it's kind of a stratified space by the different isotropy types. And we can think of it with all of its different pieces here. Okay. All right, When we want to start representing Orbispaces, there's a couple of different schemes. Originally, when orbifolds were introduced, they were introduced along the lines of manifolds, and everybody did them with charts, except that the charts could have this group action. Okay? It turns out this is like a really bad way to look at Orbispaces and orbifolds. It's really hard to just do the bookkeeping with all those charts, especially with all those group actions running around. So we're going to take a more recent point of view that was really developed by Pronk and Morday to say we're going to represent these kind of things by topological groupoids. So what that means is I'm going to have a space of objects that are just going to represent the points in my space. And then I'm going to have this space of identifications, this space of arrows that's going on. And we can actually, if we add in sort of, we make sure that if we have an identification one way, we also make sure that we have the identification the other way. And if we ensure that everybody has their identification, then we can actually put a groupoid structure on this. Okay, so we can talk about these as topological groupoids. That gives us some infrastructure for dealing with this. Now we don't go too crazy. Here's a couple of conditions that I'd like to say. That my groupoid, I would like it to be the source and target maps. We'd like them to be local homeomorphisms. Okay, and I would like the diagonal to be proper. And what that's going to do for me, those two conditions there, is it's going to constrain the types of singularities that I'm getting so that I really am dealing with what I would call Orbispaces as opposed to more general stacks or something like that. Okay, so if we look at a topological groupoid, call it an Orbi groupoid, if it is étale and proper, the implications of that are that all the isotropy groups are going to be finite, and locally the space is going to look like the quotient of an action by a finite group, like my cone point. And so then the quotient space, we're going to be thinking about it as an Orbi space, but the groupoid, all those identifications is allowing us to retain the information about the singularity type. Okay. So here's some examples of how we can represent. So a very simple thing that you might want to do is just take a point, but now have a singularity structure on your singular point. Okay, you might want to say, well, my point is identified to itself in some non-trivial way. So you could have like a whole G's worth of, for some group, you could just have that. So this would be a topological groupoid where the topology is discrete. Okay, representing my point. Okay, here's my cone represented as an Orbi groupoid. Okay, so my quotient space, that little horn over there, you can see it's turned on its side, and I've got my singularity point down at the end, and then all the other points around. I'm going to take the objects are going to just be a disk, and then the identifications, well, I'm going to have the identity morphisms, and then I'm going to identify every point with the point that's 1/3 rotation and 2/3 of rotation around. So those morphisms, I actually get 3 copies of that disk that are representing that. And you notice that the 1/3 and the 2/3 are the inverse morphisms of each other. So we actually do have a self-contained groupoid structure here. Here's a manifold example. So if you want to make a manifold with no singularities, like a unit interval or something like that, you can turn it into a topological groupoid by just taking the manifold and cloning it and saying your morphisms are only identity morphisms. Okay, done. A little bit boring, but there it is. Okay, so that's an example. Here's the unit interval in a different way. So where you're familiar with manifolds of having these sort of different atlases and refinements of atlases and covers and stuff like that, well, the groupoid allows us to capture that kind of information too. So here is a representation of that same interval where now we have 2 different components to our objects, but those 2 little short lines in the morphisms are the gluings, those identifications that say, oh, well, actually the top copy of our objects and the bottom copy of our objects should have been identified together. Okay, so there's the unit interval. And just for fun, here's the Chur groupoid. You can see that things are getting a little bit more complicated. Over on the left-hand side, you can see that we have that cone again with the disk worth of objects, and then our identity 1/3 and 2/3. And then over on the right hand side, we're going to do the other half of the the cap off of our teardrop orbifold, that's just going to be a manifold piece, so it's only going to have identity morphisms. And then just like the interval, we have to glue those together, so we've got those little annulus of gluings that say, oh, I'm going to identify the outer edge of the one disk with the outer edge of the other disk. And I actually have two annuli showing up there because, again, to make this a groupoid, once you have an identification that goes from one to the other, you need an identification that goes from the other to the one. So that's the inverse maps. Okay, so we can get that put together. Now, even in my fairly elementary examples, we've already come across the idea that there's not one single groupoid that represents an Orbispace, right? Or even in the manifold case, the interval, we had a way of breaking it up and having two different Orbi groupoids that represented the same Orbispace, okay? So we have to work with Orbi groupoids up to what we call Morita equivalence, and this is based around essential equivalences. We've actually seen this last week. This notion cropped up. I'm presenting it in a slightly different way, but it's exactly the same concept as the last time we saw this idea. Okay, so basically what we do is we take an equivalence of categories, essentially surjective and fully faithful, and we say, yes, it's that in a way that respects the topology. Okay, so that's kind of the most obvious thing that you would want to do. So you have, this is the essentially surjective part. You have to hit every orbit. You don't have to hit every point, but you have to hit every, like, some copy of that point. So if he's identified somewhere, somewhere in that orbit you have to hit. And you notice there's that open surjection in there. That's what's saying, yeah, well, it actually agrees with the topology in some sensible way. Okay. And then the same thing with the fully faithful condition that says the local structure is preserved in a way that's compatible with the topology. Okay, so that's going to be local isotropy structure in particular. So the singularity types are not changing. Okay, and then to get our full definition of Morita equivalence, well, you start off and you say, okay, well, maybe I have a zigzag of essential equivalences connecting one Orbi group to another, but actually you can cut down an arbitrary length zigzag to one that's just a span like this. So you only need one intermediate here. So this is a definition of Morita equivalent. G, K, and H are all going to be representing the exact same Orbispace for us. Okay. Okay. So the fact that we can represent our Orbispaces as groupoids allows us to say, well, we have a starting point for what maps should be. We'll just take maps of groupoids, and those are functors, just sort of the normal, you know, we take objects to objects and we take morphisms to morphisms in a compatible way, okay, and we'll make sure that everything's continuous so that we have a morphism of topological groupoids here. So that is our starting point, okay. And here's an example of how that could work and why it makes sense to be a map of Orbispaces. So here's my split unit interval over on the left, and I'm mapping it in to the teardrop orbifold. And I kind of want to just do a little path that goes around from the bottom to the top. And I'm using the split one because I have to hop from the bottom to the top there. And you can see that the objects then are down below. I go from one disk to a different disk, and then up above I have to make sure that I've glued things together so that, yeah, when I did the hop, everything was compatible. And this is, again, this is the sort of thing that we do all the time when we're dealing with manifolds. Okay. So now here's the thing about maps of Orbispaces is that every Orbispace can be represented by lots of different groupoids. Not every map can be realized by any given representation. Okay, so you might have an Orbi groupoid that represents your Orbispace and a map that will not be carried by that particular Orbi groupoid. Okay, so it gets a little bit weirder. So what we have to do is instead look at a generalized map where we say, well, G to H is illegal. I can't get a groupoid map from G to H, but maybe I can replace G with an equivalent Morita equivalent G prime, essentially equivalent G prime, where somehow G prime also represents the same Orbispace and is broken up or whatever enough to carry that map. Okay. So this is what a generalized map is. Okay, so we take our groupoid and we replace it with a different one. And here's the example, again, same example, slightly different picture, where if I wanted to say, I want to go into the teardrop orbifold from my interval, but I accidentally used the boring representation of my interval, I would not actually be able to do it. Because of that hop, I have to go from one chart to another. I have to go from the bottom piece to the top piece. Okay, so what I have to do then is take I and replace it by this equivalent, the one that's, you know, lots of colors, that's the broken interval, and say, well, that's the same Orbi space, and now it's got enough wiggle room that it can represent that path. Okay. And now, of course, we recognize that we have these generalized maps representing our maps of Orbi spaces. Now we have to think, well, when are two of these different generalized maps actually going to represent the same orbifold map? So then this is where we start getting into these bicategories. So this is a two-cell between two generalized maps. So the top, on the top, you can see the span going from G, replace it with G prime, and go over to H by a phi. And then on the bottom, take G replaced by a different G double prime, and go over by phi prime. And we want to be able to recognize when actually that really was the same thing. And everything on the left side of that thing, G, G prime, G double prime, L, are all just going to be different representations of my same Orbi space. Okay, so you can kind of think of this as being like a common refinement, if you would. Okay. And so then when we actually talk about Orbi spaces, we're talking about a bicategory of fractions, okay, where we have inverted the essential equivalences. Arrows are given by these spans. Two cells are given by these diagrams. Turns out, through a bunch of categorical voodoo with bicategories of fractions, you can actually, you don't have to look at every single two-cell diagram that you could think of. You can cut it down and say, well, I would like to pick a particular representation for, you know, like a preferred way of putting that common refinement or whatever it is in the middle. And the way that we found most convenient for dealing with the topology is actually to use the pseudo pullback square. But categorically, that's an arbitrary choice. Okay. And so if we go back to this picture here where we have our representation, if we want to change the representation, that two-cell, an example of that would be, say, instead of having our path live over in the lower right hand, maybe I want to move it around and put it in the lower left hand side. Now, in the Orbi space, that's exactly the same map, right? We would have exactly the same points coming out. We'd just be representing it in a different way, and we would actually get one of those two-cell diagrams connecting this map with that map where we moved it over to a different representation. All right, so with all of this infrastructure, then our goal is to get an exponential, a mapping space. And we had a long list of goals. First, I should say that this has been looked at before. Chen did some work with mappings for orbifolds, okay? But he didn't really define it in terms of groupoids. He was more just working with atlases, and the bookkeeping was pretty scary in some of that, okay? And then more generally for stacks, there's been work done. Karchedy has done some, and Nuhi have done some work on stacks, but again, more general context. They weren't always looking for Orbi spaces. So this is the long list of goals that we might have for this project. We want to define a topology on these generalized maps. We want to show that it's Morita invariant, so it really is a mapping space for our Orbi spaces. We might want to show that we get an Orbi groupoid, so we could actually talk about the Orbi space of maps in certain conditions. We want to show that you might want to ask whether it produces an exponential object that satisfies that standard adjunction. You might want to ask whether you can get an enriched category so that composition induces a continuous map enriched over topological groupoids or something like that. Well, step one, which is actually perhaps step 0, is that because you're dealing with these spans and the class of essential equivalences is very, very large, it's not small, you have a lot of spans. So the very first thing you have to do is cut it down to something so that you have a set that you can actually start to topologize. So that was our first move in this game, was to define this, where we cut it down to what we call an essentially covering map, which really is, so we really are thinking like every single one of these essential equivalences is, it can be swapped out for just one that we just take a covering of our original groupoid and then induce the pullback groupoid on that. Okay, so it's a locally finite collection of open subsets, and then we just sort of cut it down like that. Okay, and it turns out, again, bicategorical voodoo kicks in, and we do, in fact, the class of essential covering maps will give us a bicalculus of fractions that's equivalent to the original. So we can only work with, we can just work with these spans that are given by this particular form. In particular, we'll get Hom categories that are small. Okay, so that's our first move. Okay, our second move is now we're going to have to start making some assumptions for things to work. We're going to require that our our Orbispaces be orbit compact. So we're going to get some compactness requirements. And in that case, these essential coverings, then we can actually get down to finite coverings. Okay. And then we can just kind of follow our nose and do a topology on this exponential. So our topology on this space of objects is just going to be, so we've got all these spans, but really we've only got finite coverings now, and we'll just take disjoint union indexed over finite essential coverings, and we just use the compact open topology coming from on each of the pieces. Okay, and then we have to worry about the space of arrows, which is these spans, and again, where the topology is coming from here, that's a big messy thing down at the bottom, but really the first thing is really topologizing the phi, and this third thing is really topologizing the psi, and then the middle part is topologizing the beta. Okay, so we've managed to kind of pull the left-hand side, at least, out of the topology and just have it as an index. Okay. So we're topologizing this big thing. All right, well, so that's what works. So we were wondering whether we could get an Orbi groupoid. We kind of get half a one. We get that it's a proper groupoid, but it might not be étal. It is an exponential object, so that adjunction works. That's great. Enrichment, continuity of composition, difficult to say. I don't think we can swear that it doesn't, but we certainly can't prove that it does. Okay, so then our next move is to say, well, let's see if we can do better. Again, slap some extra assumptions on it, paracompact, locally compact. We go back and we look at what Chen did in his results. Now, again, he was not quite topologizing the Orbi groupoids. Okay, he was more just working. He managed to get an enrichment for the quotient space, but not over the entire Orbi groupoid kind of thing. But we sort of pulled some of his inspirations for this from there. And so we have a new kind of span, which is called admissible. And so these are kind of relatively compact. And so we can restrict now even further to these things called admissible spans. Okay. Now, we get a full subcategory. Here's the trick is that you don't actually want to take the subspace topology on this, okay? So instead, you kind of want to do this voodoo where you choose a little bit of a shrinkage, a nice open set that's contained in it, but such that phi extends to its compact closure and stuff like that. Anyways, it's a little delicate, but I think I will not belabor that point and just say there is a way of getting an inclusion from the right inclusion as an open map from A map to O map. It's not the subspace topology, but it does work. And then we look at A map and see where have we gotten to. Well, A map is an Orbi groupoid, given our various compactness assumptions. So that's great. We have ourselves a mapping Orbi space. It's still the exponential. That's awesome. Okay. It's Morita invariant. We can prove that it's actually Morita invariant. So it really is a mapping object for Orbi spaces. And then the last thing on my wish list was enrichment, the composition function being continuous. It's not over Orbi groupoids. And for a while, we were very sad and thinking that we had failed completely. But then we realized that actually it was continuous if we enriched over Orbispaces rather than topological groupoids, meaning that we can get a continuous generalized map from the product AMAP GH and AMAP HK over to AMAP GK. If we're allowed to put something in the middle, which we've been doing all along, we can actually get this to be nicely enriched over Orbispaces. And yeah, so I think I'm pretty much out of time. So I think I'll stop there.
Thank you very much, Laura. So are there any questions, comments?
I can ask one.
Yeah.
Just to clarify a bit, are you localizing at the admissible maps? Are you considering the localization at the admissible maps or only at the essential equivalences?
I think we're still localizing at the essential equivalences.
Okay.
But we're just doing this voodoo with the topology.
Got it. They only play a role when you do the topology, not when you do the fractions.
That's right.
Okay, thank you.
Yeah, actually, so we do one step in between, but comes down to almost the same thing. So we do localize at the essential covering maps. They actually allow for localization still. But then when we make them admissible, we just playing the game locally. And we haven't actually looked, maybe you can do a full, but the thing is that because...
Yeah, I don't think we've actually tried.
Sorry?
I don't think we've actually tried.
No, and the thing is, it only makes sense for compact orbifolds, so you have to restrict yourself further. But yeah, I think it might be possible. We just haven't actually looked at that.
Right now, we're just playing games with the topology.
Yeah.
Thanks.
Any other question? Okay. Well, we thank Laura again.